So let's continue then with a shared presentation from Alejandra De La Hija. I don't know if I pronounce your name correctly, and Andrea Friso later on, both talking about binder jet technology with the first presentation on functioning and working. So Alejandra currently works in the HP Hewlett-Packard 3D print team in Barcelona as an application engineer for the new HP MetalJet S100 solution. She joined HP's team 5 years ago as procurement engineer and vendor manager. Prior to HP, she worked for various companies in the automotive industry, both in Germany and United Kingdom, developing projects and products as mechanical engineer. She holds a Master of Science in Mechanical Engineering by the Universidad Politécnica de Madrid, and also is part of the mentorship program Inspira STEAM in Spain to inspire young students to follow technical careers. In her presentation, she is talking about MetalJet technology that represents a new approach to metal powder additive manufacturing of metal parts, well established and proven across several industrial sectors for production of stainless steel-based applications. MetalJet is currently being introduced also to the world of jewelry, and this is why you're here, and fashion industry to unlock and open up new opportunities and manufacturing options. This presentation will deal with the concepts behind binder jetting, the enabling processes, and unique applications of a MetalJet printer. So, we look forward.
Hello, good morning, everybody. So yeah, as my colleague was saying, my name is Alejandra De La Hija. That's the way to pronounce it, so you are not that far away. I work as an application engineer for Hewlett-Packard for HP, specifically for 3D metals printing. To give a little bit of background, yeah, I'm short. To give a little bit of background, in HP, we have the headquarters for additive manufacturing in Spain, in Barcelona, although we split the development between the US team and the Spain team, but the core of the technology is basically developed in Spain. I work as application engineer, so my job is to work very closely with customers that want to use our technology and help them in the design process, in the development process, until the parts are ready and stable in mass production. Before we go too deep and technical into the technology, I want to explain a bit the journey that we have been going through since we started to develop the technology. So binder jet technology was born many, many years ago in the MIT. It's a technology that we have been studying for many years already at HP as an incubation technology. But it was in 2018 when we finally announced that HP was going to invest in this technology because we saw a lot of potential to be able for the first time to manufacture 3D printed metal parts at scale with quality, productivity, and cost efficiency. So in 2018, we finally announced that we were going to develop this technology, and how we developed this technology was by strong partnerships with key players from the industry. So in 2020, we already started conversations with Legor to understand how we could impact in the jewelry industry as well. And we've been testing with Legor for a couple of years, parts, products, materials, so far and so on. And finally, in March 2022, we proceed to the installation of the first units in Legor. And also, an important milestone for us is that in September this year, we finally announced publicly that our final solution is commercially available for every customer that wants to invest in this technology. How we are working with customers, it's a double approach. So we want to be very close to the OEMs, which basically are the companies that have designs that can be produced with our technology. These can be companies from every single industry. And these companies, some of them will want to have a vertical integrated manufacturing, meaning that they will be producing their parts in-house with their own printers. But many of them will just want to buy the parts from strategic partners. So that's why we keep on growing our network of partnerships with contract manufacturers or with experts powder development, like Legor. So we like to be in the middle because we've been in contact with customers from all the industries for many years, and we understand well how to communicate with customers and how to be able to transfer projects to contract manufacturers.
Right, done that.
He seems to be ready. So here I present you our solution. We don't like it. We don't like calling it only a printing solution. It's an end-to-end solution for the mass production of metallic parts. You see in the middle the printer itself, but on the sides you see also the powder handling solutions, which we believe it's very important to have in order to automatize as much as possible all the process of the powder handling. So the focus of the development of the technology has been from day one productivity, cost efficiency, and quality to really be able to produce at mass production volumes metallic parts. Before I explain in detail BinderJet, I wanted to give you a little bit an overview of what are the current additive manufacturing technologies. We have here a graph that's evolving every year. I was this year at Formnext. I was surprised to see all the many new technologies that are coming in the additive world. But I think when looking at specifically metals, which is the sign that you can see in the bottom, like with a magnet sign, there are three key players. You have directed energy deposition, which probably was the oldest 3D printing technology developed for metals. Basically, it's a robotic arm that deploys metal powder fused with a filament and with a laser or an electron beam. It's quite old. It's mostly used for very big parts. The quality, it's a little bit questionable on this technology. Then probably you are all quite familiar with powder bed technologies, most commonly known as laser technologies, which are probably the most stable technology right now in the market because it's been for many years in the market. The bottleneck for laser printing is productivity and cost efficiency. So for prototypes, normally it works well. It keeps on increasing the productivity, but scaling products at mass production with cost efficiency, it's a little bit of the bottleneck of the technology. So that's why BinderJet was born. You see it in the middle. This is where HP has developed their own solution. It really helps to create, to have very good productivity and to tackle mass production volumes. Not working anymore. The next slide, it's a bit heavy in size, so maybe that's why it's taking some time. Okay, here we go. So what is the process itself? Here we say HP MetalJet, but it's quite generic to BinderJet in general. So we start by spreading a layer of very thin metal powder over the build platform in the printer. And then we come with print heads, very common, very similar to the ones that you will have in your printers at home, that put ink exactly where you want to print the part. We do this it's a surface-based process, so basically with one pass of the print heads, you are printing the full area that you want to be printing. The ink that we deposit in this technology, we call it a binder. Binder, which is basically a glue that glues the metal particles together. So we keep on doing this layer by layer. Basically, you will come, you will spread another layer of powder, you will put again the ink using our print heads, and you need to do this by applying a certain level of energy. Why you need to apply a little bit of energy is because our ink is a water-based ink, and you need to start evaporating part of the solvents from this ink. Also, it's important to apply energy because you don't want the ink to go into further layers. You want the ink to fix in the layer where you are exactly printing in each exact moment. So basically, once you finish the printing process, you do layer by layer with the print heads, putting the ink. You need to apply even more energy because this ink is basically a polymer, and you need to cure the polymer to make sure that the chain of the polymer is really activated and you are activating the glue mechanism of the polymer chain. So you apply this energy, which we call the curing process, And finally, what you have is basically a box that's filled with powder that has not been printed and parts that have been printed. We call these parts green parts. It will be similar to the brown parts in powder metallurgy, which are still not fully dense, which are still not fully sintered, because basically the metal particles are only glued together. So once you do the excavation process, this means you take out the parts that have been printed and you retake the powder that has not been printed, so you can reuse it in the next cycle. You apply finally a sintering conventional cycle to the part, and you obtain the final solid part. To this part, in the last image, what you can see is you can do any post-processing that you will do to any other metallic part. You can post-machine the part if needed. You can heat-treat the part even more if you need to. You can polish the part. Any other thing that you will do to any other conventional metallic part, you can do to binder jet parts. So what's the advantage of additive manufacturing in general over conventional metal? It's, I think, the most important key benefit is freedom of design. So it helps to generate very innovative products that with conventional technologies, it will be quite hard to produce. Also, it's important to think about how fast you can iterate many different options, because you can print many different designs at once, and you can qualify them, you can validate them in parallel as well. And most importantly, it's a tool-free process, so you don't have the pains that you will have in product development with conventional technologies, because you don't need to invest in expensive tools. What is binder jet bringing to the additive manufacturing industry in general? It's the productivity and also the raw materials. So basically, productivity is clear because, as I was mentioning, it's an area-based process, so you are printing the full area with one pass of the recoater of the printhead, compared to laser, where you have to be printing point by point each single particle. Also, another advantage is that since you are sintering the full mass of the part in the furnace together, you get very isotropic properties compared to laser printing. And finally, since you are printing only green parts in the printer, you can stack parts vertically in the printer without the need of printing supports, which means that you reduce also the processing steps that you will require with conventional laser printing. Important to highlight as well is the metal powders. We are leveraging the ways of producing the metal powders that are used in metal injection molding. This helps to really reduce the raw material cost significantly as well, which in the end drives the part cost as well. And what is metal jet, HP's metal jet advantage over binder jet ecosystem in general? The way I like seeing binder jet, it is the most similar 3D printing process to paper printing, because instead of printing with your printheads in paper, basically you are printing with your printheads in a powder base. So we have been, at HP, we have been printing in paper for more than 40 years, and all that knowledge that we have in-house has been put in the development of our exclusive binder jet technology. We are leveraging our knowledge on printheads, and we are leveraging our knowledge on inks to create this binder that we have in the market today. How the process works itself. In the previous slide, I was commenting how the printing process works and how the current printing process works, which are the two middle pictures you have here. But this is not the only solution that we have developed. As I was mentioning, if we want to drive part quality, if we want to drive productivity, it's important as well to automatize as much as possible the powder handling process. So how we start, basically we start either with fresh metal powder or with recycled metal powder. We can use both, we can use a combination of both as well. And you will load your build unit. The build unit is the small unit that you see in between the different stations, which is where the metal powder is traveling and where the printed parts are traveling. So basically, we have first our powder management station, which helps to mix and sieve and have very homogeneous powder distribution in the full powder that you are loading. And you will load automatically this build unit that will be ready to be printed. You will take, it's a card with wheels, you will take this card, you will insert it in the printer, and you will start with your printing process. When you are done with the printing process, you will need to move to the curing station. We do the curing station separately away from the printer because we want the printer to be doing 24/7 what it does best, which is printing. So we consider curing is not what the printer does best. So that's why we do the curing in a separate curing station. Once you have the parts cured, which means the binder is activated, the metal particles are glued together, you will need to do the depowdering. Of course, you can do the powdering manually with vacuum system, with an operator, but this will take long time. So for low volumes, this makes sense, but when you are thinking about high productivity, it makes sense to use our automatic depowdering station, which with our combination of airflow and vibration helps to depowder the parts so they are ready to be taken and to put in the sintering furnace for the final sintering process. As I was saying, all the powder that's collected from the depowdering station can be put in our portable tanks and be reused in the next cycle, because basically the metal powder in the printer, it's only heated up to 70 degrees, so there is no damage being done to that powder, so it can really be recycled without issues. Now, why we chose this technology in particular? So when we look at the portfolio of technologies that exist in the market and the market size, it's an 800 billion market size in mass production of metal parts. $800 billion with technologies that have not been really disruptive for decades. So we have metal injection molding, investment casting, press and sinter, machining, forging, stamping, joining, and welding. The newest technology was metal injection molding that was put in place in the 70s. And since then, no new technology has come in the market to really try to disrupt the production of metallic parts. So that's why we saw a niche there to be able to create parts with innovative designs, design freedom that could disrupt the production of metallic parts. Each single current technology has its own pain points. So when you are thinking about producing a part with binder jet, it's important to understand which pain point you are trying to overcome from these technologies. Because if you are just trying to substitute a machine part with a binder jet part with the same design, most likely you will not be successful. Machining is very stable technology. So if you are looking into machining, for instance, a very complex geometry, you have a lot of material waste, it doesn't really make sense to machine that part, maybe that part is a good fit for binder jet. So it's important to look at which pain point you are killing from each single technology. So the product can be successful in binder jet. It can be that you need to iterate faster. It can be that you don't want to invest in tooling because you have maybe low volumes in production and you don't want to make that huge investment in tooling. So the key benefits, the way I see it, for binder jet in general, are the ones that you see here in the bottom, which basically is to enable new geometries, to have design freedom. Also, it's important to look at part consolidation. Many times you have many hours of assembly time with conventional technologies that maybe you don't need to have with our technology, because you can print several parts at once and print several functionalities at once as well. When looking into jewelry, customization is for free, so you can customize every single product for free because you can print all of those parts together in a digital way. So customization in the jewelry industry could be quite interesting as well. We are enabling new sizes, especially we compare with MIM. The largest MIM part in the world weighs around 400 grams. We can produce parts that weigh up to 1 kilo. So in some cases, we are actually enabling also new sizes. When looking at surface quality, it's also important to highlight that binder jet in the portfolio of additive manufacturing techniques is the technique that enables better surface quality. And specifically with our solution, what we are told by customers is that we are able to achieve very good surface roughness compared to other technologies as well. And finally, the turnaround time. So as I was saying, you can qualify, you can develop many products at once because you can print them together. We have a customer that's very happy about using our technology because previously it was taking them up to 2 years to go to market with a new product, and with our technology it's taking them only 6 months to develop new products. So this is something interesting to look into as well with additive. Now, which parts are a good fit for the technology? I think it's important, this is not rocket science, but I think it's important to understand really that this is a technology that has been developed for mass production of parts. So if you are looking only to create a prototype of one single part and then move to a different technology, binder jet is not going to be the right fit for that part. So it's important to think about components that will be serialized with the technology to take the full advantage of the productivity that the technology can offer. Then looking at size and shape, it's important to look maximum recommended size that we give is a tennis ball size or a fist size of a part, because like this you can put many parts in a printer and take the full advantage of the productivity. We can print, of course, bigger parts than that, but maybe from a cost point of view, it will not be so efficient. Then from a weight point of view, as I was saying, we can produce parts of up to 1 kilo. Over 1 kilo, the sintering becomes a little bit challenging. So when looking at products that weigh even more than 1 kilo, we can look into topological optimization, look into ways to reduce the weight to put the product into the spec, let's say. Also, it's very important to look at how the product can be stacked in the printer. So if it stacks very nicely, you can put many different components in the printer, which will help to drive the economics down as well. I was talking as well about product complexity, and many customers tell us, but how do you measure a complexity of a product? It's not easy to measure the complexity, but a way to see it is imagine that design, imagine how you will CNC machine that part, and if you require more than 4 and 6 tool changers or setups in the CNC center, that's a design that's complex enough to consider binder jet technology for that one. And then finally, a little bit of design recommendations. The main bottleneck from a design point of view is the sintering process. During the sintering, you are really heating the material to a point that's very close to the melting point, so you have effect of the gravity acting over that design. So it's very important to think about how that design is going to be supported during the sintering process, and we can help on that thinking as well. From a design point of view, you were seeing it in the previous slide, more than half of the industry in metal production is produced with machining. So designers for metal parts are very used to think about machining, which basically you start from a block and then you start removing material. With additive, it's the other way around. You start creating material from layer by layer, basically. So you will need to think about what are the interfaces and add material only wherever you need it, not think the other way around about creating a block and remove material by a CNC machine, let's say. When talking about the wall thicknesses, the minimum recommended wall thickness is around 1 millimeter. We can go lower than that in specific cases, but the minimum recommended is around 1 millimeter, and it's important to have uniform wall thickness as well, transitions. This coming from the sintering as well, otherwise you will see distortions that are not wished. And finally, looking at small features, pins, holes, cavities, so far and so on, also the recommended size is around 1 millimeter.
Yeah, thank you very much for this very good introduction into the binder jet technology.